Picture this: a force so powerful it can rip atoms apart from thousands of miles away, bending the very fabric of space itself. Out there in the cosmos, hidden among the stars, lurk magnetic fields with strengths beyond anything we could ever recreate on Earth. These invisible giants shape the universe in ways that defy imagination, from the crushing depths of neutron stars to the explosive hearts of distant galaxies. Today, we're diving into one of the most extreme and mysterious phenomena in existence, the universe's most intense magnetic fields. And trust me, what we're about to uncover will bend your mind as much as these fields bend reality. Think of the strongest magnet you've ever encountered, maybe one that held up a fridge note or sent pins flying across a room. Now multiply that power by 100 trillion, and you're still only scratching the surface. Neutron stars, the collapsed cores of dead stars, pack magnetic fields so intense they can heat matter to millions of degrees in an instant. These cosmic powerhouses don't just attract metal. They warp light, twist space-time, and generate energy bursts visible across the universe. And yet, they're just one piece of a much larger puzzle. From the explosive dynamos of black holes to the vast magnetic webs stretching between galaxies, these forces are the invisible architects of the cosmos, shaping everything from star birth to the fate of entire solar systems. But how do these magnetic fields form? What happens when they collide or snap? And could they hold the key to some of the universe's greatest mysteries? Over the course of this journey, we'll uncover 30 astonishing facts about these cosmic powerhouses, facts that will challenge everything you thought you knew about magnetism, energy, and the raw power of the universe. So buckle up. We're about to venture into realms where physics as we know it breaks down, where the laws of nature twist into something stranger than fiction, and where the universe reveals its most extreme and beautiful secrets. Ready to have your mind pulled in directions you never expected? Let's begin. Among the countless wonders of the cosmos, magnetars stand in a league of their own, stellar corpses so magnetically ferocious they could wipe out life on a planet halfway across the galaxy. Born from the ashes of supernova explosions, these neutron stars pack the mass of our Sun into a sphere no wider than Manhattan, spinning at dizzying speeds while harboring magnetic fields a quadrillion times more powerful than Earth. If you could somehow stand on the surface of one, though you'd be instantly vaporized, the force would pull the iron from your blood and distort the very atoms in your body before you even had time to blink. Take SGR 180620, a magnetar that made headlines in 2004 when it unleashed a gamma ray burst so energetic it temporarily ionized Earth's upper atmosphere from 50,000 light-years away. For a fraction of a second, this single star outshone the entire Milky Way, releasing more energy than our Sun will emit in 250,000 years. And yet, that cataclysm was just a hiccup in the life of a magnetar, a stellar tantrum from an object whose magnetic field is constantly on the verge of tearing itself apart. What makes these objects so unstable? The answer lies in their turbulent birth. When a massive star collapses, its core doesn't just shrink, it twists. Like a figure skater pulling their arms in to spin faster, the star's magnetic field gets wound tighter and tighter, amplifying to unimaginable levels. But unlike Earth's relatively stable magnetic shield, a magnetar's field is a knotted, chaotic mess. It's constantly under strain, building tension until without warning, it snaps. These starquakes crack the magnetar's crust, sending shockwaves through space-time and blasting jets of radiation across the cosmos. Astronomers compare magnetars to cosmic time bombs, ticking away with the potential to rewrite the rules of physics. Their magnetic fields are so intense they create exotic states of matter unseen anywhere else, where particles align in impossible ways and light itself bends into strange loops. Some theories suggest they might even warp the quantum vacuum, producing particle-antiparticle pairs from empty space. And here's the chilling part: Our galaxy likely harbors dozens of these dormant monsters, silently spinning in the dark, any one of them capable of flickering to life with apocalyptic consequences. Yet without them, we might never glimpse the true extremes of nature, the places where magnetism stops being a force and becomes something closer to magic. To grasp the sheer scale of these cosmic magnets, let's put the numbers in perspective. Earth's magnetic field, the invisible shield protecting us from solar radiation, measures about 0.5 Gauss. That's roughly the same strength as the humble fridge magnet holding up your grocery list. Now imagine a neutron star where magnetic fields can reach 10 to the 15th Gauss. That's a 1 followed by 15 zeros. The difference between Earth's field and a neutron star's is like comparing a candle flame to the heart of a supernova. Picture this: if you could somehow bring a teaspoon of neutron star material to Earth, its magnetic field would be powerful enough to rip every credit card, hard drive, and electronic device on the planet to shreds from 1,000 miles away. It would exert enough force to yank a battleship out of the ocean and hurl it into orbit, not gradually, but in a fraction of a second, even more mind-bending. That same magnetic field could distort the trajectory of a speeding bullet mid-flight, bending its path as easily as gravity bends light. Here's another way to visualize it. The atomic bombs dropped on Hiroshima released energy equivalent to about 15,000 tons of TNT. A neutron star's magnetic field stores as much energy as 1 million of those detonations happening simultaneously every single second. Yet despite this unimaginable power, these fields remain invisible, detectable only by their extreme effects on the space around them. They twist the paths of charged particles, generate swirling auroras in dead star atmospheres, and even slow the star's rotation over time like cosmic brakes made of pure force. What's truly astonishing is how these magnetic monsters influence space far beyond their surfaces. A neutron star's magnetic field doesn't just stop at its crust, it extends light years into space, weaving intricate patterns in the surrounding nebula. Charged particles spiral along these invisible lines like cars on a cosmic freeway, emitting intense radiation we can detect across the galaxy. And when these fields shift or collapse, they don't just flicker. They unleash tsunamis of X-rays and gamma rays, rewriting the rules of particle physics in real time. In the grand theater of the universe, neutron stars aren't just actors, they're the directors, bending the stage itself to their will. While neutron stars showcase magnetism at its most extreme, our own sun demonstrates that even familiar cosmic objects hide astonishing magnetic secrets. Every 11 years, like clockwork, the sun performs a spectacular disappearing act. Its north and south magnetic poles swap places in an event that would make any compass spin wildly if we could stand on the solar surface. This polar flip isn't some orderly transition either. The sun's magnetic field gets tangled like a ball of yarn in a hurricane before finally snapping into its reversed configuration, unleashing chaos across the solar system in the process. During these reversal years, sunspots multiply like freckles across the sun's face, marking regions where concentrated magnetic energy boils up from deep within. These aren't your average dark spots, each one could swallow Earth whole, with magnetic fields thousands of times stronger than our planet's protective shield. When particularly unstable sunspot groups collide, they trigger solar flares equivalent to millions of hydrogen bombs detonating simultaneously. The most powerful of these eruptions, called coronal mass ejections, hurl billions of tons of magnetized plasma into space at millions of miles per hour. One such storm in 1859, the Carrington event, set telegraph offices ablaze and produced auroras so bright birds started singing at midnight, thinking dawn had arrived. What makes the sun's behavior so extraordinary compared to Earth's own magnetic reversals, scale and frequency? While our planet takes between 70,000 and 1 million years to flip its poles, with the process spanning thousands of years, the sun accomplishes this feat in just months, like a cosmic gymnast performing a perfect backflip. The reason lies in the Sun's churning plasma interior, where electrically conductive gases act like a dynamo, constantly regenerating and rearranging magnetic fields. This creates a dramatic cycle where solar activity builds to a violent peak before the magnetic field abruptly reorganizes itself, resetting the clock for another 11-year roller coaster. The consequences reach far beyond spectacular light shows. Modern society depends on technologies vulnerable to these solar tantrums. GPS satellites can lose accuracy, power grids face overload risks, and astronauts outside Earth's protection absorb dangerous radiation doses. Yet this same magnetic chaos also gives rise to the Sun's breathtaking corona, that shimmering halo visible during total eclipses. Temperatures there inexplicably soar to millions of degrees, heated by the constant snapping and reconnecting of magnetic field lines in a process scientists still struggle to fully explain. The Sun reminds us that even the most ordinary-looking star in our sky remains a dynamic, unpredictable beast, one whose magnetic personality shapes the very space we live in. Jupiter isn't just the solar system's largest planet. It's home to a magnetic monster that dwarfs everything else in our cosmic neighborhood. Imagine a field so vast it could engulf the Sun if it were visible to the naked eye, stretching over 7 million kilometers into space. That's Jupiter's magnetosphere, a turbulent force 20,000 times stronger than Earth's, where charged particles whip around at nearly the speed of light. This isn't just a planetary magnetic field, it's a celestial powerhouse with enough energy to accelerate electrons into lethal radiation belts, creating an invisible death zone no spacecraft can penetrate for long. Take the Juno probe, which braved Jupiter's magnetic jaws in 2016. To survive, it had to adopt an elliptical orbit that ducked beneath the worst radiation, like a surfer navigating towering waves. Even then, the spacecraft's camera suffered constant electronic snow from particle bombardment, while its instruments recorded electric currents strong enough to power entire cities flowing through the gas giant's atmosphere. But the real spectacle happens at Jupiter's poles, where its magnetic field funnels charged particles into the most intense auroras in the solar system, permanent light shows that could outshine 100 Earths. These aren't the gentle green ribbons we see on our planet, but ultraviolet infernos hotter than the Sun's surface, stretching wider than our entire world. What fuels this magnetic behemoth? Deep beneath Jupiter's cloud tops, hydrogen gets crushed under such immense pressure that it morphs into a bizarre metallic liquid, swirling like a cosmic dynamo. This metallic hydrogen ocean, possibly mixed with helium rain, generates electric currents as Jupiter rotates at breakneck speed, completing a day in just under 10 hours. The resulting magnetic field doesn't just protect Jupiter. It dominates the space around it, stretching so far that its tail brushes Saturn's orbit when the two giants align. Along the way, it ensnares Jupiter's moons in a deadly embrace, particularly volcanic Io. Io's tortured relationship with Jupiter's magnetism reads like a cosmic horror story. As the most volcanic body in the solar system, it spews a ton of sulfur dioxide into space every second, material that gets ionized and caught in Jupiter's magnetic grip. This creates a donut-shaped plasma torus around Jupiter, a river of superheated gas where particles collide with enough force to generate radio waves we can detect on Earth. Meanwhile, magnetic flux tubes, invisible tunnels of energy, connect Io directly to Jupiter's poles, pumping 50 trillion watts of power into the planet's atmosphere. That's enough electricity to supply human civilization for centuries, all generated by a moon being slowly cooked in its parent planet's magnetic furnace. Yet for all its violence, Jupiter's magnetic field plays a crucial protective role. Without it, the solar wind would have stripped away much of the planet's atmosphere over billions of years, just as it did to Mars. Instead, Jupiter stands as a cosmic shield, its magnetism deflecting dangerous particles away from its inner moons, though Europa and Ganymede have developed their own magnetic quirks in response. The gas giant reminds us that magnetism isn't just about attraction and repulsion. It's a dynamic force that shapes worlds, accelerates particles to extreme energies, and paints the sky with light shows no artist could ever replicate. Binary star systems take cosmic magnetism to terrifying new heights, especially when one of those stars is a neutron star with an appetite for destruction. Imagine a celestial spider spinning magnetic webs to slowly consume its partner, and you've got the Black Widow pulsar, a neutron star that lives up to its ominous name. This cosmic predator, officially known as FRB 1957+20, doesn't just orbit its companion, it bombards it with magnetic winds so intense they're literally boiling the star away at 5,000 miles per second. Here's how this lethal dance unfolds. The pulsar's magnetic field, already strong enough to shred atoms, gets supercharged by its rapid spin, over 600 rotations every second. As it whips around, it flings charged particles into space like a cosmic sprinkler, creating a hurricane of plasma and radiation. But its companion star, a lightweight roughly the mass of Jupiter, is trapped in this storm, just 2 million miles away, closer than some asteroids ever get to Earth. The pulsar's magnetic fury heats the star's surface to 12,000 degrees Celsius, stripping away 800 million tons of material every second. Over time, this relentless assault will leave nothing but a wisp of gas where a star once shined. What makes binary systems like this so extreme? It's all about synergy. The neutron star's rotation injects energy into its magnetic field, amplifying it far beyond what a solitary pulsar could achieve. Meanwhile, the stolen stellar material gets funneled along magnetic field lines, crashing onto the pulsar's surface at nearly light speed and triggering X-ray bursts bright enough to outshine entire galaxies for brief moments. Astronomers call these millisecond pulsars neutron stars spun up to dizzying speeds by their cannibalistic habits. The Black Widow's partner won't just fade quietly either. Its death throes create bizarre conditions where magnetic fields warp light so severely that the star's shadow appears stretched across space like a cosmic mirage. And the Black Widow isn't alone. Systems like PSRJ 0317+0541 feature neutron stars with magnetic fields so twisted they act like particle accelerators, firing beams of antimatter into space. Others, like Terzan 5A-D, have magnetic wakes that stretch light years behind them, visible as eerie blue trails in radio telescopes. These binary monsters push magnetism into realms where it ceases to behave like a simple force, instead acting as a sculptor of stellar corpses, a catalyst for intergalactic fireworks, and ultimately the architect of cosmic oblivion. While individual stars and planets showcase extreme magnetism on small scales, the Milky Way hosts a magnetic masterpiece spanning 100,000 light-years, an invisible scaffold shaping everything from newborn stars to rogue cosmic rays. Unlike the violent fields around neutron stars, our galaxy's magnetism whispers rather than roars, with strengths barely 1/1,000,000th of Earth's protective bubble. Yet spread across such epic distances, this delicate force orchestrates the motion of entire gas clouds and steers high-energy particles like a cosmic traffic controller. Astronomers map this colossal web using a phenomenon called Faraday rotation, where the galaxy's magnetic field subtly twists the polarization of radio waves passing through it. Picture light traveling from distant quasars, those brilliant galactic cores billions of light-years away. As their radio waves traverse the Milky Way, interstellar electrons spiraling along magnetic field lines act like celestial corkscrews, gradually rotating the wave's orientation. By measuring these twists across different sky regions, scientists have reconstructed our galaxy's magnetic skeleton in stunning detail, revealing giant loops and filaments weaving between spiral arms. What emerges is a dynamic tapestry unlike anything near Earth. Near the galactic center, magnetic fields churn like storm clouds, twisted by the supermassive black hole's gravitational tides. Further out, the fields align more orderly along the spiral arms, guiding collapsing gas clouds into stellar nurseries. Some regions resemble melted glass, with field lines frozen into interstellar plasma during ancient stellar explosions. Others show bizarre reversals where the magnetic polarity flips abruptly, like finding patches of compasses pointing south instead of north across a continent. This magnetic architecture does more than create pretty maps. It's a cosmic shield regulating the galaxy's ecosystem. Charged particles zipping through space cosmic rays accelerated by supernova get deflected by these fields, preventing them from sterilizing entire star-forming regions. Meanwhile, the fields themselves provide scaffolding for molecular clouds, subtly encouraging gas to clump into protostars. Without this galactic magnetism, star formation might proceed in chaotic bursts rather than the steady rhythm we observe. One of the most breathtaking consequences appears near the galactic poles, where the Milky Way's magnetic field funnels escaping particles into vast chimneys. These structures, stretching 25,000 light-years above and below the disk, act like exhaust pipes for cosmic rays, and their shapes reveal the field's surprising flexibility. Unlike the rigid fields around magnetars, the galactic magnetic web bends and reconnects constantly, responding to stellar winds, supernova shocks, and even the gravitational tug of satellite galaxies. It's a living network, reshaping itself on timescales of millions rather than nanoseconds, yet no less wondrous for its patience. The next time you gaze at the Milky Way's starry band across the night sky, remember, you're not just seeing stars and dust. You're witnessing the visible traces of an invisible masterpiece, a magnetic canvas so vast it makes Jupiter's mighty field look like a fridge magnet, quietly orchestrating the galaxy's grand evolution one particle at a time. Earth's magnetic field has been our silent protector for millennia, an invisible shield deflecting deadly solar radiation and cosmic rays, allowing life to flourish beneath its embrace. But this vital defense system is faltering. Measurements over the past 2 centuries reveal our planet's magnetic field has weakened by nearly 10% overall, with one region deteriorating so rapidly it's earned an ominous nickname, the South Atlantic Anomaly. Stretching from Chile to Zimbabwe, this vast zone where Earth's magnetic protection dips to just 1/3 its normal strength is growing wider each year, expanding westward at about 12 miles annually. Satellites passing through this magnetic pothole experience what engineers call single-event upsets, sudden computer glitches caused by intense radiation bombardment. The Hubble Space Telescope actually powers down its instruments when traversing the area to avoid permanent damage. Astronauts aboard the International Space Station report seeing strange flashes of light behind their eyelids here, caused by cosmic rays directly stimulating their optic nerves. These eerie effects offer a preview of what could happen if Earth's magnetic decline continues unchecked. A future where once protected regions face radiation levels matching high-altitude flight, with consequences for technology, ecosystems, and human health. The roots of this magnetic crisis trace deep underground to the turbulent sea of molten iron swirling around Earth's core. Here, where temperatures match the sun's surface, the geomagnetic dynamo generates our protective field through complex fluid motions. But something is disrupting this cosmic engine. Satellite data reveals startling patterns, whirlpools of magnetism spinning backwards beneath southern Africa, massive plumes of dense material rising from the core mantle boundary. Some scientists believe these anomalies signal the early stages of a magnetic pole reversal, where north and south flip positions, a phenomenon that occurred hundreds of times in Earth's history, but never during human civilization. During past reversals, which can take centuries to complete, the magnetic field might weaken to just 10% of its current strength. Without this shield, increased radiation could trigger more frequent mutations in surface-dwelling organisms, disrupt animal navigation systems, and render large swaths of the planet inhospitable to current electrical grids. Already, airlines reroute flights over the South Atlantic anomaly to limit crew radiation exposure, while power companies monitor for geomagnetically induced currents that could fry transformers. The most vulnerable infrastructure, undersea internet cables whose repeaters sit directly in the anomaly's path. A single powerful solar storm during a magnetic minimum could sever global communications for weeks. Yet Earth's magnetic story isn't one of inevitable decline. The same processes eroding our shield also hint at its resilience. Deep beneath Brazil, researchers discovered a strange, dense structure called the Africa Large Low Shear Velocity Province, acting like a magnetic brake shoe against the outer core's motion. Meanwhile, rapid field changes spotted beneath Canada suggest localized regeneration could offset global weakening. Like a planetary immune system responding to threat, our dynamo may already be developing new defenses. We just can't yet predict their ultimate form. What remains certain is this: we're witnessing a planetary transformation unprecedented in recorded history, playing out not in centuries but decades, with consequences we're only beginning to understand. Imagine invisible rubber bands stretching across space, storing unimaginable energy as they twist and tangle until suddenly they snap. This explosive moment, when magnetic field lines break and violently reconnect, powers some of the most dazzling displays in the cosmos. Scientists call it magnetic reconnection, a process so efficient at converting stored magnetic energy into heat and motion that it makes nuclear reactions look sluggish by comparison. NASA, a magnetospheric multiscale mission, a quartet of spacecraft flying in perfect formation, has captured this phenomenon in action, revealing electron-scale details of a process that can light up planets and vaporize solar material in seconds. Take a typical solar flare. Deep in the sun's churning atmosphere, magnetic field lines from different regions collide and become entangled, building up energy like a coiled spring. When the tension becomes unbearable, the fields abruptly reconfigure, releasing enough energy in minutes to power human civilization for millennia. The MMS mission witnessed a scaled-down version of this near Earth, where the solar wind's magnetic field interacts with our planet's protective magnetosphere. Their measurements showed electrons accelerating to nearly light speed in just 15 milliseconds faster than any human-made particle accelerator could achieve. These aren't gentle nudges but violent slingshot effects, where charged particles get catapulted along newly formed field lines at velocities approaching 60,000 kilometers per second. What makes reconnection so transformative? It's all about topology. Picture two sets of magnetic field lines moving toward each other, like lanes of traffic merging. Normally, they'd repel like same pole magnets, but under the right conditions, they instead break and form new connections, like highways suddenly exchanging on ramps. This topological shortcut converts magnetic energy directly into particle motion and heat, bypassing slower processes like friction. The resulting energy dump can heat plasma to tens of millions of degrees while flinging material across interstellar distances. The consequences shape our cosmic environment. When reconnection occurs in Earth's magnetotail, the elongated downwind side of our magnetic field, it injects energized particles into the upper atmosphere, sparking auroras that dance across polar skies. But the same process also threatens astronauts and satellites during solar storms. In 2015, MMS observed electron-scale jets, narrow beams of particles fired like cosmic bullets during reconnection events. These jets carried thousand-fold more energy than predicted, explaining why solar flares can abruptly escalate from minor flickers to planet-shaking eruptions. Perhaps most astonishing is reconnection's role beyond our solar system. Around black holes and neutron stars, magnetic fields get stretched into unimaginable configurations, storing enough energy to power relativistic jets shooting across galaxies. Even the solar system's heliosphere, the vast magnetic bubble separating us from interstellar space, owes its shape to ongoing reconnection at the boundary where the solar wind collides with galactic material. Far from being a destructive force, magnetic reconnection emerges as the universe's preferred method for recycling magnetic energy, fueling everything from the gentlest auroral glow to the most violent cosmic explosions. Among the quiet embers of dead stars, white dwarfs often seem like tame cosmic relics until you meet ones with magnetic personalities that defy all expectations. Take GD356, a white dwarf so magnetically charged it makes Earth's field look like a faint whisper, clocking in at 100 million times stronger than our planet's protective bubble. This stellar corpse doesn't just have a magnetic field, it wields it like a cosmic sculptor, warping space around it with such intensity that light itself bends to its will. What makes stars like GD356 so extraordinary? Imagine a dying star that's collapsed into an Earth-sized ember, yet retains a magnetic grip so fierce it can rip apart the very fabric of nearby atoms. Most white dwarfs cool quietly over billions of years, but magnetic variants like this one rewrite the rules. Their fields are strong enough to trap their own atmospheres in bizarre polar prisons, creating bright, isolated caps of gas at each magnetic pole while the rest of the star's surface remains eerily bare. It's as if someone took a planet's auroras and cranked them up to stellar scale, permanently freezing the spectacle in place. The origins of these magnetic monsters remain one of stellar astrophysics' great puzzles. Some theories suggest they're born from the mergers of two white dwarfs, their combined magnetic fields amplifying during the violent collision. Others propose these fields were always there, buried beneath the star's surface during its active life, only to emerge like a hidden weapon when the outer layers blew away. Whatever the cause, the effects are undeniable. The magnetic field around GD356 is so intense it splits spectral lines, the fingerprints of elements in its atmosphere into triplets, a phenomenon so rare it was initially mistaken for evidence of an exotic quantum state. Here's where things get even stranger. Unlike neutron stars, whose magnetic fields often power violent jets and radiation storms, these white dwarfs wield their magnetism with eerie precision. Their fields shape the motion of charged particles so completely that atoms can't even tumble freely. They align like soldiers in formation, vibrating only along magnetic field lines. This creates conditions where convection, the usual process that transports heat in stars, gets overridden entirely. The result, a star that doesn't cool evenly but instead develops mysterious hotspots locked in magnetic stasis. Perhaps most astonishing is how these magnetic titans influence their surroundings. Any planets that survived the star's death throes would find themselves in a cosmic funhouse, where compass needles would spin uselessly and auroras would blaze not just at the poles but in strange, shifting rings. Dust and debris orbiting the star wouldn't form neat disks, they'd be funneled into intricate spirals along magnetic pathways, like iron filings trapped in a celestial sculpture. Even light passing nearby would twist under the field's influence, a phenomenon called vacuum birefringence predicted by quantum electrodynamics, but observable only around such extreme objects. Yet for all their power, magnetic white dwarfs like GD356 are cosmic anomalies. Fewer than 1 in 10 white dwarfs show such extreme magnetism. Their rarity makes them invaluable laboratories for testing physics at limits impossible to recreate on Earth. Each new discovery peels back another layer of their mystery, revealing the hidden ferocity lurking within even the quietest seeming stars. As astronomers continue to study these magnetic relics, they're finding that a white dwarf's retirement may be anything but peaceful, especially when it's armed with a force capable of bending the very rules of reality. Fast radio bursts are among the most enigmatic signals in the universe's cosmic screams, so intense they outshine entire galaxies for milliseconds before vanishing without a trace. For years, these fleeting blips of radio energy puzzled astronomers, appearing random and undecipherable. Then came FRB 121102, the first repeating fast radio burst ever detected, flickering from a dwarf galaxy 3 billion light-years away. This wasn't just another cosmic oddity, it was a smoking gun hauntingly close to a region swirling with extreme magnetism, where theorists suspect a magnetar might be lurking behind the chaos. What makes this particular burst so extraordinary? The answer lies in its neighborhood. The host galaxy of FRB 121102 crackles with star-forming fury, birthing massive stars destined to collapse into magnetars, the perfect breeding ground for magnetic havoc. When astronomers pinpointed the burst's origin, they found it nestled near what could only be described as a magnetic maelstrom, a dense magnetized nebula likely powered by a young neutron star. The repeating pattern of these bursts, sometimes firing off multiple signals in an hour, then falling silent for months, hints at something even more bizarre. Unlike one-off FRBs thought to come from catastrophic collisions, this repeater behaves like a malfunctioning cosmic lighthouse, its beams sporadically sweeping across Earth as its magnetic environment convulses. The leading theory, a magnetar caught in an endless tantrum. Picture a neutron star with a magnetic field so twisted it periodically snaps like an overstretched rubber band, each rupture unleashing a torrent of energy. These magnetic reconnection events could accelerate particles to near light speeds, generating shock waves that produce the radio bursts we detect. Supporting this idea, observations revealed FRB 121102's signals are nearly 100% polarized, a telltale sign of radiation passing through an intensely magnetized environment. It's as if the bursts are being filtered through a cosmic prism made of pure magnetic force. But magnetars alone might not explain everything. Some bursts show weird downward frequency drifts, like a radio dial slowly turning, suggesting the signals are battling through clouds of magnetized plasma near the source. Others exhibit complex substructure with multiple peaks crammed into a single millisecond, implying intricate magnetic geometries around the central engine. Then there's the elephant in the room. A handful of FRBs now appear to originate from relatively quiet galaxies with no obvious magnetar factories. Could there be multiple flavors of these bursts, some tied to magnetic monsters while others stem from entirely different phenomena? The most tantalizing clue came in 2020, when a magnetar within our own galaxy SGR 1935+2154 erupted with a radio burst suspiciously similar to an FRB, albeit weaker. This marked the first direct evidence linking magnetars to these cosmic signals, yet it deepened the mystery. The galactic magnetar's burst was thousands of times fainter than extragalactic FRBs. If magnetars are indeed responsible, some must unleash energies far beyond anything we've witnessed nearby, perhaps aided by surrounding debris or hyper-magnetized nebulae amplifying their fury. As telescopes like CHIME and FAST discover hundreds more FRBs, patterns emerge that no single theory can yet explain. Some repeat with clockwork regularity, others explode once and vanish forever. A few even arrive with gamma-ray counterparts, suggesting connections to neutron star mergers or black hole births. But for FRB 121102 and its kin, the evidence keeps circling back to extreme magnetism, an invisible force twisting space, accelerating particles, and sculpting some of the most fleeting yet luminous signals ever detected. Whether these bursts are magnetars screaming into the void or something even stranger, they're forcing us to rewrite our understanding of magnetic extremes in the cosmos. Deep within stellar nurseries like the Orion Nebula, newborn stars perform an astonishing cosmic balancing act. They feed on swirling disks of gas and dust while simultaneously hurling jets of material light years into space. The secret behind this contradictory behavior: magnetic fields woven through the protostellar disk like invisible puppet strings, orchestrating the chaotic dance of star formation with precision. Take HL Tau, a young star 450 light-years away that's become a Rosetta Stone for understanding this process. Thanks to unprecedented images from the ALMA telescope array, we can now see how its magnetic field channels material into neat spiral arms, like cosmic conveyor belts feeding the growing star while also launching twin jets at nearly 500,000 miles per hour. These aren't just any magnetic fields, they're dynamic force networks operating on scales that dwarf our solar system. Picture a disk stretching 15 billion miles across, where every particle of dust aligns like a compass needle to reveal the field structure. As gravity pulls material inward, the magnetic field resists, creating a celestial tug-of-war that shapes the disk into concentric rings. The ALMA images of HL Tau show this vividly dark gaps between bright bands where fledgling planets may be coalescing, all sculpted by magnetic forces. But the real magic happens at the poles, where the field lines twist into helical coils. These act like particle accelerators, funneling ionized gas into narrow jets that punch through interstellar clouds, carrying away excess angular momentum so the star can keep growing. The process resembles a cosmic water wheel. As material spirals toward HL Tau, the magnetic field transfers its rotational energy upward, accelerating particles until they escape along open field lines. These jets glow brightly in radio wavelengths, their shock waves heating surrounding gas to thousands of degrees. Without this magnetic pressure release valve, the star would spin itself apart before reaching maturity. Even more remarkably, the same fields that launched jets also shepherd dust grains into planet-forming regions. ALMA detected dust particles 10 times larger than in interstellar space, already clumping together in HL Tau's rings. This suggests magnetism doesn't just build stars, it sets the stage for planetary systems in their earliest moments. Yet protostellar magnetic fields aren't static. They fluctuate wildly as the star evolves, sometimes pinching off entire chunks of the disk into independent plasmoids. In 2018, astronomers observed one such event around protostar Karma 7, a magnetic bubble detaching from the disk like a runaway elevator, carrying enough mass to form a gas giant planet. Other systems show even more extreme behavior, like ERAS 43147, where the magnetic field has warped the disk into a pretzel shape, creating chaotic accretion streams that fuel violent growth spurts. What makes HL Tau special is how clearly its magnetic architecture is imprinted on its surroundings. The star's jets trace perfect parabolic curves across 2 trillion miles of space, while dust grains in the disk align in telltale patterns visible in polarized light. These grains, some coated in icy organic molecules, spin like tiny tops as they respond to the field, potentially influencing the chemistry of future planets. It's a humbling realization. The same forces directing star birth may also determine whether a forming world gets water, complex molecules, or the raw ingredients for life. Far from being passive bystanders, magnetic fields emerge as master sculptors, shaping stellar cradles into planetary systems, one precisely guided particle at a time. Imagine a world where the very atoms in its core could be crushed into glittering diamond, not by heat or pressure, but by the invisible lash of a dead star's magnetic fury. Meet PSR J1719-1438b, a planet so bizarre astronomers jokingly call it the Diamond Planet, though its story is anything but precious. Orbiting a pulsar just 4,000 light-years away, this celestial oddball started life as a star itself, only to have its outer layers violently stripped away, leaving behind a corpse so dense its carbon-rich core may have crystallized into a planet-sized diamond under the pulsar's relentless magnetic assault. This isn't your typical planetary formation. The Diamond Planet's pulsar parent spins over 10,000 times per minute, whipping its magnetic field into a frenzy that bathes the planet in radiation equivalent to standing inside a particle accelerator. That same field, 1 trillion times stronger than Earth's, does something even stranger. It induces electric currents deep within the planet, effectively turning its interior into a cosmic induction furnace. The result, carbon atoms forced into rigid crystalline lattices, potentially creating a diamond core hundreds of miles across. But here's the twist. This glittering heart might be locked in a magnetic vise so tight the diamond can't even conduct heat, turning the planet into a paradox. A scorching hot icebox where surface temperatures exceed 2000 degrees Fahrenheit while its interior remains eerily cold. The pulsar's influence doesn't stop at diamond making. Its magnetic field acts like a cosmic sculptor, distorting the planet's atmosphere, what little remains, into a teardrop shape trailing behind it. Spectroscopic studies suggest this atmosphere might contain exotic carbon compounds like graphene or even long-chain polymers, essentially plastic rain whipped sideways by magnetic winds. Meanwhile, the pulsar's radiation sandblasts the planet's surface with such intensity that it likely sparkles with metallic carbon crystals, reflecting light like a disco ball in the cosmic void. What makes this system truly exceptional is its origin story. Most pulsar planets are thought to form from the debris of destroyed companion stars, but PSR J1719-1438b appears to be the Grim Reaper's handiwork, the leftover core of a white dwarf that wandered too close to its pulsar partner. The pulsar's gravity siphoned away the white dwarf's outer layers until only this dense, carbon-rich remnant survived, now trapped in a death spiral that could one day see it completely vaporized by its undead host. Until then, it serves as a laboratory for extreme physics, where magnetic fields don't just influence matter, they redefine its very nature. Astronomers speculate there could be thousands more of these magnetic oddities lurking in our galaxy, each a testament to the transformative power of pulsar magnetism. Some might harbor diamond cores even larger than Earth, while others could be forged into stranger configurations, perhaps lattice-like carbon structures unknown on Earth, or even superconductive metallic hydrogen layers constrained by the pulsar's field. Whatever their forms, they remind us that in the universe's most extreme environments, even the hardest substances we know become putty in magnetism's invisible hands, reshaped, reordered, and reborn under forces we're only beginning to comprehend. While most planets in our solar system wobble with magnetic fields tilted at odd angles, Saturn stands apart as a cosmic anomaly. Its magnetic field aligns with near-perfect symmetry to its rotation axis, a precision so exact it defies current planetary science. Unlike Earth, where compasses point 11 degrees away from true north, or Uranus, which rolls around the Sun with its magnetic poles aimed almost sideways, Saturn's invisible shield behaves like a perfectly balanced top. The Cassini spacecraft, during its 13-year orbit around the ringed giant, revealed this peculiarity while simultaneously deepening the mystery. How can a gas giant spinning at 30,000 kilometers per hour maintain such flawless magnetic alignment when every known dynamo theory predicts turbulence? The answer may lie beneath Saturn's cloud tops, where hydrogen transforms into a bizarre metallic fluid under crushing pressures, while Jupiter's dynamo churns in distinct layers, creating patchy magnetic zones. Cassini's measurements suggest Saturn's internal engine operates with unsettling smoothness. One theory proposes that helium rain, condensing and falling toward the core like a celestial drizzle, stabilizes the magnetic field by suppressing chaotic convection currents. Another posits that Saturn's deep interior hosts a hidden giant, a stable layer of electrically conductive material, perhaps a soup of hydrogen compounds, acting like a magnetic flywheel to keep the field steady. The most tantalizing clue came from gravity data. Saturn's core might be fuzzy, blending gradually into the metallic hydrogen envelope rather than having a sharp boundary, allowing for seamless energy transfer. This symmetry has breathtaking consequences. Saturn's auroras, unlike Earth's dancing lights or Jupiter's raging tempests, form near-perfect circles around both poles, halos of charged particles spiraling obediently along those exquisitely aligned field lines. Even Saturn's rings feel the magnetic order, microscopic ice particles there become electrically charged and get lifted by magnetic forces into a ghostly ring rain that spirals down toward the planet's equator. Cassini spotted this phenomenon in ultraviolet light, a shimmering band of infalling material guided by the planet's impeccable magnetic geometry. Yet perfection comes at a price. Saturn's magnetic field, while flawlessly aligned, is surprisingly weak compared to Jupiter's, just 1/20th the strength despite being only slightly smaller. This suggests Saturn's dynamo operates in a delicate balance, possibly stabilized by conditions that also limit its power. Some researchers speculate this might be a temporary state, over millions of years as helium continues separating from hydrogen deeper inside. Saturn's field could eventually tilt and strengthen like Jupiter's. For now, it remains a cosmic oddity, a planet where magnetism and rotation move as one, challenging our understanding of how celestial magnetic engines truly work. The implications stretch beyond Saturn. Exoplanets with similar alignments might hide oceans of metallic hydrogen or exotic phases of matter we've yet to discover. And if helium rain really does stabilize magnetic fields, it could explain why some gas giants evolve into perfectly symmetrical beacons while others become magnetically chaotic monsters. Saturn's quiet precision reminds us that even in the violent cosmos, elegance can emerge not from simplicity, but from forces so complex they cancel out into perfect harmony. Galaxies don't drift through space alone, they gather in sprawling metropolises called clusters, where thousands of galaxies swarm like bees in a hive. But between these glittering islands lies something far stranger, a superheated sea of gas threaded with magnetic fields powerful enough to reshape entire cosmic neighborhoods. Take the Coma Cluster, a mammoth gathering of galaxies 320 million light-years away. Its intracluster medium crackles with magnetic energy so intense it bends the paths of high-speed particles like a cosmic obstacle course. This intergalactic magnetic web isn't just a faint whisper. It's a dynamic force field with strengths up to several microgauss. That might sound insignificant compared to a refrigerator magnet, but spread across millions of light-years, it becomes a dominant player in the cluster's ecology. Charged particles zipping through space, cosmic rays accelerated by supernova or active black holes get tangled in these fields like fish caught in invisible nets. Their trajectories twist into spirals as they interact with the magnetized gas, causing them to linger in the cluster rather than escaping into intergalactic space. The result, a vast reservoir of high-energy particles sloshing between galaxies, kept in check by magnetism's invisible hand. How do astronomers detect something so intangible? The secret lies in radio telescopes and an effect called Faraday rotation. When light from distant quasars passes through the Coma Cluster's magnetized plasma, its polarization twists just as a prism bends visible light. By measuring how much each wavelength rotates, scientists can reconstruct the cluster's magnetic architecture in stunning detail. What emerges is a turbulent tapestry, fields stretched and folded by galactic motions, with filaments that align along shock fronts where galaxies collide. Some regions show magnetic knots 100 times denser than average, likely amplified by the violent orbits of massive elliptical galaxies plowing through the gas. These cosmic magnetic webs do more than corral particles. They shape the cluster's very evolution. The fields act like scaffolding, supporting filaments of gas against gravitational collapse and influencing where new stars can form. They also regulate heat flow. Magnetic waves carry energy from the cluster's scorching center, reaching 100 million degrees to its cooler outskirts, preventing runaway cooling that could trigger chaotic star formation. Without this balancing act, the Coma Cluster's galaxies might drown in torrents of condensing gas, birthing stars at unsustainable rates. Perhaps most astonishing is how these fields originated. Unlike galaxies, where magnetism arises from swirling plasma in stars and interstellar gas, clusters had no obvious dynamo to generate such vast magnetic structures. One leading theory suggests they grew from faint seed fields present in the early universe, perhaps stretched and amplified by cosmic inflation, then further energized by galactic winds and supernova explosions over billions of years. Another proposes that active supermassive black holes at galaxy centers pumped magnetic energy into the intracluster medium like cosmic fire hoses, their jets inflating magnetized bubbles that eventually merged into today's web. The implications reach far beyond the Coma cluster. Similar magnetic signatures have been found in other massive clusters like Abell 4059 and the Perseus cluster, where fields align along gargantuan sound waves rippling through the gas, the aftermath of ancient black hole eruptions. These discoveries hint that magnetism might be a universal feature of cosmic structure, as fundamental to galaxy clusters as dark matter or hot gas. They also offer clues to one of astrophysics' great mysteries, the origin of ultra-high-energy cosmic rays, particles so energetic they shouldn't exist under current physics models. Some researchers speculate that cluster magnetic fields could act as natural particle accelerators, boosting these rare projectiles to impossible speeds over cosmic distances. As telescopes like the Square Kilometre Array come online, astronomers anticipate mapping these magnetic labyrinths in unprecedented detail, revealing how they connect to larger-scale cosmic filaments and influence the growth of galactic superstructures. Already, simulations suggest that without intracluster magnetism, the universe would look radically different. Galaxies might clump more densely, star formation rates could vary wildly, and even the distribution of dark matter might be subtly altered. The Coma cluster and its kin remind us that magnetism isn't just a local phenomenon, it's woven into the fabric of cosmic society on the grandest scales, silently orchestrating the dance of galaxies across eons. December 27, 2004, a date that marked one of the most violent cosmic outbursts ever recorded, originating from a dead star halfway across our galaxy. SGR 180620, a magnetar nestled in the constellation Sagittarius, unleashed what astronomers call a giant flare, a magnetic explosion so ferocious it momentarily outshone the full moon. For 1/5 of a second, this single collapsed star released more energy than our sun radiates in 250,000 years, emitting a gamma-ray pulse so intense it temporarily altered Earth's upper atmosphere from 50,000 light-years away. Satellites designed to detect nuclear explosions lit up as if the planet had been struck by a nearby supernova, while radio blackouts rippled across the globe as the flare's X-rays ionized our ionosphere, reflecting long-range radio signals into space like a cosmic mirror. What makes magnetar flares so catastrophically powerful? The answer lies in a process called magnetic reconnection, but on a scale that dwarfs anything seen on the Sun. Picture a neutron star's crust made of crystalline neutronium harder than diamond, buckling under the strain of twisted magnetic field lines. Like tectonic plates on Earth, this crust occasionally fractures in starquakes, releasing pent-up energy equivalent to thousands of earthquakes. But here's where magnetars differ. Their magnetic fields are so intense that when the crust cracks, the entire magnetic structure snaps like an overwound rubber band. The resulting explosion doesn't just emit light, it rips pairs of electrons and positrons from empty space itself, creating a fireball of particle-antiparticle plasma trapped in the magnetar's grip. The 2004 event wasn't an isolated incident. Only 3 such giant flares have been confirmed in observational history, one in 1979 from the Large Magellanic Cloud, another in 1998 from SGR 1900+14, and this 2004 monster. Each follows a terrifyingly consistent pattern, an initial spike of gamma rays reaching 10 million times the sun's brightness, followed by pulsating afterglows that can last minutes as the magnetar's magnetic field restructures itself. The pulsations reveal the star's frenzied rotation as JR 180620 spins once every 7.5 seconds, its jet-like lighthouse beam of radiation sweeping across space with each turn. What's truly chilling is how these flares propagate through the cosmos. Unlike supernovae that radiate energy in all directions, magnetar flares focus their fury into narrow beams, cosmic blowtorches capable of sterilizing planets thousands of light-years away if Earth happened to lie in their path. Had the 20,004 flare occurred within 10 light-years nearby in galactic terms, it could have triggered a mass extinction by stripping our ozone layer and bombarding the surface with lethal radiation. Even more unsettling, our galaxy likely harbors dozens of dormant magnetars, any one of which could unleash a similar cataclysm without warning, their eruptions detectable across intergalactic distances. Yet within this chaos lies a scientific goldmine. The 20,004 flare's subtle effects on Earth's atmosphere allowed researchers to measure its total energy output with unprecedented precision, equivalent to detonating a 1-megaton nuclear bomb for every square mile of the magnetar's surface. Its pulsating afterglow provided the first direct evidence of Unveil waves, magnetic ripples theorized in 1942 but never before observed in nature. And the flare's rapid decay helped confirm quantum electrodynamics predictions about how light interacts with ultra-strong magnetic fields. These observations are rewriting textbooks, proving that magnetars aren't just celestial oddities. They're natural laboratories for physics at the extreme, where the universe bends the rules beyond recognition. Venus presents one of the solar system's greatest ironies. A planet nearly identical to Earth in size and composition, yet devoid of the global magnetic field that protects our atmosphere. While Earth's molten core churns like a dynamo, generating a protective magnetic bubble, Venus spins so sluggishly it completes just one rotation every 243 Earth days. This lack of motion stifles the planetary engine needed to sustain a magnetic shield, leaving the planet exposed to the full fury of the solar wind. Without this protection, charged particles from the Sun slam into Venus' upper atmosphere at hundreds of kilometers per second, gradually stripping away its gases like sandblasting a statue. The consequences play out dramatically in Venus' ionosphere, where solar winds ionize atmospheric molecules, creating a comet-like tail of escaping particles stretching millions of kilometers into space. NASA Pioneer Venus Orbiter first documented this atmospheric hemorrhage in the 1980s, detecting oxygen and hydrogen atoms being ripped away at a rate of about 100 metric tons per hour. Over billions of years, this relentless erosion may explain why Venus, once potentially harboring Earth-like oceans, now bakes under a suffocating blanket of carbon dioxide 90 times thicker than our air. The planet's present atmosphere could be merely the scorched remains of what it once possessed, its water vapor dissociated by sunlight and its hydrogen lost forever to the solar wind's magnetic currents. What makes Venus' predicament even stranger is its geological resemblance to Earth. Radar mapping reveals possible tectonic features and volcanic plains, suggesting its interior once hosted molten metal capable of magnetism. Some scientists speculate that Venus might generate localized, short-lived magnetic fields during volcanic eruptions, brief flickers of protection quickly overwhelmed by the solar onslaught. Others propose its upper atmosphere fights back through induced magnetism, where solar wind particles interacting with Venus' ionosphere create a weak secondary magnetic layer. While this buffer slows atmospheric loss, it's like holding up a sheet of paper against a hurricane compared to Earth's robust global field. The European Space Agency's Venus Express mission uncovered another twist: Venus' atmospheric escape isn't steady. During periods of heightened solar activity, the rate of loss can spike tenfold, with entire clouds of ionized oxygen surging into space like a planetary hemorrhage. These bursts correlate with interplanetary magnetic field alignments, proving that even without its own dynamo, Venus remains deeply entangled in the Sun's magnetic web. Solar storms don't just erode the atmosphere, they electrify it, generating auroras without a magnetic field, ghostly ultraviolet glows dancing across the planet's night side. Understanding Venus' magnetic failure holds urgent lessons for exoplanet research. Among potentially habitable worlds, slow rotators like Venus may outnumber Earth-like spinners, making their atmospheric stability precarious. The boundary between a life-nurturing oasis and a sterilized wasteland might hinge on the presence or absence of a churning metallic core. Venus stands as a cautionary tale of how even twin planets can meet radically different fates, separated by something as invisible as magnetism. Beneath the surface of a neutron star, the laws of physics as we know them warp into something stranger than fiction. The crust, a crystalline lattice of neutron-packed atomic nuclei, becomes a quantum playground where magnetism twists space itself into microscopic vortices. These aren't just magnetic fields, they're tornadoes of pure force, each one trillions of times stronger than Earth's entire magnetic shield, squeezed into a space smaller than an atom. When these vortices tangle and snap, the resulting starquakes release more energy than all the world's nuclear arsenals combined, in bursts of X-rays astronomers can detect across the galaxy. Take the case of SGR 0418 plus 5729, a neutron star that suddenly brightened by a factor of 10,000 in 2009, not from external forces but from internal magnetic turmoil. Deep in its crust, quantum vortices had formed an elaborate network resembling a cosmic spiderweb, with magnetic tension building between each intersection point. When one critical link finally fractured, the entire structure recoiled like a broken spring, vibrating the star's surface at frequencies that sent shockwaves racing through nearby space-time. The event lasted barely a tenth of a second, yet in that blink of cosmic time, it converted magnetic stress into enough X-rays to outshine a supernova. What makes these quantum vortices possible? Neutron star crusts exist in a state physicists call nuclear pasta, neither solid nor liquid but an exotic arrangement where atomic nuclei deform into strands, sheets, and bubbles under unimaginable pressures. Into this bizarre landscape seep protons freed from decaying neutrons, forming superconducting currents that generate microscopic magnetic whirlpools. Each vortex carries a quantum mechanical stamp called magnetic flux quantization, meaning they can't gradually weaken, only snap abruptly when strained too far. This gives neutron star crusts properties unlike any known material, elastic like rubber yet harder than diamond, and capable of storing magnetic energy for years before catastrophically releasing it. The detection of these starquakes revolutionized astrophysics by providing the first observational evidence for quantum magnetic phenomena on cosmic scales. X-ray telescopes like NASA have clocked vibrations from these events with staggering precision, some ringing at 575 Hz, meaning the star's surface ripples 575 times per second. To put that in perspective, Earth's most powerful earthquakes max out at fractions of a single hertz. The frequency patterns act like cosmic tuning forks, letting astronomers probe the crust's composition. Some neutron stars show harmonics suggesting their crusts are layered like onions, with different quantum vortex configurations at varying depths. Perhaps most mind-bending is how these microscopic events influence the star's global behavior. A single quantum vortex snap can trigger chain reactions, realigning entire magnetic domains in the crust. This might explain why some magnetars suddenly change their rotation rates not gradually as expected, but in abrupt glitches where the star speeds up by 1 part in a million seemingly overnight. It's as if the crust acts like a quantum-scale capacitor, storing magnetic stress until the vortices collectively rebel, briefly unlocking the star's superfluid interior to transfer angular momentum outward. These quantum quirks aren't just theoretical curiosities, they shape observable cosmic fireworks. In 2006, Neutron star XTJ1810-197 produced an X-ray burst followed by 40 days of pulsating afterglows, a rhythmic decay pattern matching precisely with quantum vortex reconnection models. Even more remarkably, some starquakes emit not just X-rays but gravitational waves, ripples in space-time detectable by observatories like LIGO. We're essentially feeling the aftershocks of quantum events happening 15,000 light-years away, a testament to how neutron stars amplify microscopic physics to cosmic proportions. Far from being inert dead stars, neutron crusts emerge as dynamic quantum laboratories, places where magnetism doesn't merely exist, but dances in steps dictated by the universe's most fundamental laws. Each crack in their crystalline veneer offers a fleeting glimpse into physics operating at energy regimes we could never recreate on Earth, proving that sometimes the universe's most extreme secrets hide not in vast cosmic structures, but in the infinitesimal twists of quantum magnetic threads. The Crab Nebula isn't just a beautiful remnant of a star's violent death, it's a cosmic particle accelerator operating on a scale that makes human-built colliders look like toys. At its heart spins a pulsar, the collapsed core of the star that exploded in 1054 AD, blasting out a shockwave so bright ancient astronomers recorded it as a daytime star visible for weeks. But what makes this stellar graveyard truly extraordinary isn't just the pulsar's rapid spin 30 times per second, but the magnetized hurricane it whips up around itself, a phenomenon known as a pulsar wind nebula. This turbulent zone stretches over 10 light-years, its intricate filaments glowing with the energy of particles surfing on magnetic waves at over 99.9% the speed of light. The process begins with the pulsar's intense magnetic field, a trillion times stronger than Earth's, acting like a colossal electric generator. As the pulsar rotates, it drags magnetic field lines through surrounding space, creating enormous voltages that rip electrons and their antimatter counterparts, positrons, straight out of the vacuum. These particles get flung outward along the pulsar's equator in a dense, magnetized wind, forming a donut-shaped torus visible in X-ray images as a faint blue ring. But the real spectacle happens where this wind slams into slower-moving debris from the ancient supernova explosion, a collision zone marked by an intricate web of glowing filaments. Here, something remarkable occurs. The pulsar wind's magnetic field becomes tangled and amplified as it interacts with the supernova remnant, forming shock fronts that act like natural particle accelerators. Electrons spiraling along these chaotic field lines emit synchrotron radiation, the same process that powers particle accelerators on Earth but on a cosmic scale. The result, a neon-hued labyrinth where particles gain energies exceeding 10 quadrillion electron volts, producing light across the entire electromagnetic spectrum, from radio waves to gamma rays. The crab's eerie blue glow in visible light comes from these ultra-relativistic electrons, while its wispy tendrils trace the paths of magnetic flux tubes frozen into expanding gas. This magnetic mayhem isn't just for show, it shapes the nebula's evolution. The pulsar wind inflates a bubble within the supernova debris, pushing against the surrounding material while magnetic pressure prevents the bubble from collapsing. Over centuries, this has stretched the nebula into an oval shape, with jets of particles firing from the pulsar's poles like cosmic blowtorches. These jets, visible as faint spikes in Hubble images, carve through the nebula at half the speed of light, their paths guided by the pulsar's magnetic axis. Meanwhile, knots of material within the nebula brighten and fade as magnetic reconnection events dump energy into localized regions. Stellar lightning storms visible from 6,500 light-years away. What makes the Crab a Rosetta Stone for astrophysicists is how it bridges the gap between theory and observation. In 1968, radio astronomers discovered the nebula's rapidly spinning pulsar, confirming a then controversial prediction that supernovae leave behind neutron stars. Later observations revealed how its magnetic field acts like a dynamo, converting rotational energy into particle acceleration with staggering efficiency. The pulsar loses enough energy each second to power Earth's electricity consumption for 750,000 years. Yet despite this steady drain, the nebula's magnetic turbulence ensures the energy spreads unevenly, creating bright hotspots where particles slam into denser filaments. The crab's influence extends beyond its visible structure. Its pulsar wind nebula serves as a natural laboratory for studying extreme plasma physics, conditions impossible to recreate on Earth. Satellite measurements show how magnetic fields channel particles into intricate patterns, while gamma-ray telescopes catch flares suggesting magnetic reconnection events capable of boosting electrons to petaelectronvolt energies in milliseconds. Some theorists even speculate that supernova remnants like the crab could be the birthplaces of mysterious ultra-high-energy cosmic rays particles arriving from space with energies surpassing anything human accelerators can produce. As we watch the Crab Nebula evolve, its filaments expanding outward at nearly 1,500 kilometers per second, we're witnessing magnetism's enduring power to sculpt chaos into beauty. The same forces that once tore a star apart now orchestrate its afterlife, turning a cloud of debris into a luminous testament to the universe's invisible architecture. Far from being a static monument, the crab remains a dynamic work in progress, its magnetic brushstrokes still painting the cosmos nearly a millennium after the star's final cry. Imagine a planet where compasses spin wildly, unable to find true north because the magnetic poles don't even align with the planet's rotation. This is the bizarre reality of Uranus and Neptune. Unlike Earth's relatively tidy magnetic field emerging from its poles, these ice giants wield magnetic fields that look as though they were designed by a drunken cartographer. Uranus in particular spins nearly on its side, with its axis tilted a staggering 98 degrees, essentially rolling around the Sun like a cosmic bowling ball. But the real surprise came when Voyager 2 zipped past in the 1980s, revealing that its magnetic field isn't just tilted, it's lopsided, offset from the planet's center by nearly a third of its radius. What could cause such cosmic asymmetry? The answer lies beneath these planets' thick atmospheres, in slushy oceans of superionic water, a bizarre state of matter that's neither fully liquid nor solid. Under the crushing pressures inside Uranus and Neptune, water molecules break apart, with oxygen atoms forming a crystalline lattice while hydrogen ions flow freely like a conductive soup. This creates a dynamo unlike anything in the rocky planets or gas giants, one that doesn't operate in a neat metallic core, but in a vast churning mantle of electrically charged slush. The chaotic motion of this material, combined with the planet's rapid rotations, generates magnetic fields that are powerful yet strangely disorganized, like a poorly wound electromagnet. Neptune's magnetic field, while slightly less extreme than Uranus, still defies expectations. Its magnetic axis tilts 47 degrees from its rotational axis, and the field's origin point is similarly offset. This leads to a magnetic environment where auroras don't neatly circle the poles but flicker unpredictably across the planet's atmosphere. Even more intriguing, both planets' fields are far from static. Voyager detected intense, short-lived magnetic disturbances, suggesting their dynamos might be prone to sudden reconfigurations, almost as if their internal engines periodically sputter and misfire. Why does this matter? These wonky magnetic fields offer a glimpse into the hidden interiors of ice giants, a class of planet that dominates the Milky Way. Astronomers now suspect worlds like Uranus and Neptune may outnumber gas giants like Jupiter in our galaxy, making their magnetic quirks a common cosmic feature rather than an anomaly. Their lopsided fields also challenge our understanding of dynamo theory. proving that planetary magnetism can emerge from conditions radically different from Earth's molten iron core. One tantalizing possibility is that these offset fields actually stabilize the planet's atmospheres against solar wind erosion. While Earth's symmetrical field creates a predictable shield, Uranus and Neptune's skewed fields might generate a more chaotic but equally effective barrier, their ever-shifting lines of force scattering incoming charged particles like a celestial pinball machine. This could explain why these distant worlds, despite their strange magnetism, have retained thick atmospheres over billions of years. The next time you gaze at the night sky, remember, out beyond Saturn, two blue enigmas whirl through the darkness, their invisible magnetic fingerprints as unique as cosmic snowflakes, proof that even something as fundamental as planetary magnetism can take forms stranger than we ever imagined. Beyond the orbits of Pluto and the Kuiper belt, where the solar wind's influence finally wanes, lies one of the most dramatic magnetic frontiers in our solar system, the magnetic highway. This turbulent zone marks where the sun's outstretched magnetic arms shake hands with the interstellar medium, creating a cosmic no-man's land first witnessed by Voyager 1 in 2012. As the spacecraft pierced this boundary, its instruments detected something extraordinary: charged particles from our solar system streaming outward along magnetic field lines like cars merging onto an interstellar freeway, while galactic cosmic rays flooded inward from deep space. The physics behind this phenomenon reads like a cosmic tug-of-war. The sun's magnetic field, carried outward by the supersonic solar wind, inflates a protective bubble called the heliosphere that envelops all the planets. But as this bubble expands, it encounters the interstellar magnetic field, a web of forces threading the Milky Way. Where these two magnetic systems collide, they don't just stop, they reorganize. Solar magnetic field lines connect with galactic ones in a process called magnetic reconnection, creating open pathways that allow particles to escape our solar system or invade it. Voyager's data revealed these connections form a structured network, with solar particles accelerating to nearly light speed as they funnel onto the highway toward interstellar space. What makes this region so astonishing is its dynamism. Unlike the static boundary scientists once imagined, the magnetic highway pulses with activity as the sun moves through different interstellar environments. During periods of high solar activity, the highway widens with more solar particles escaping and cosmic rays deflected. During quiet solar periods, it narrows like a constricting throat. Voyager detected sudden surges in cosmic ray intensity as it crossed this zone, moments when the interstellar magnetic field temporarily overwhelmed solar defenses, offering previews of the galaxy's raw particle radiation. The most startling discovery: this magnetic handshake zone isn't smooth, it's frothy. The clashing magnetic fields generate enormous bubbles, each about 150 million kilometers wide, where field lines break and reconnect chaotically. These structures, predicted by simulations but confirmed only by Voyager's passage, act like magnetic foam, filtering and redirecting particles in ways that challenge traditional astrophysics models. Some solar particles get trapped in these bubbles for months before finding an exit, while cosmic rays zigzag through them like pinballs. For space weather scientists, the magnetic highway offers crucial insights. Its behavior helps predict how galactic cosmic rays, which can threaten astronauts and satellites, penetrate our solar system. The highway also serves as a preview of what future interstellar probes might endure, revealing how spacecraft shielding must handle not just solar radiation but the galaxy's more potent particle bullets. Perhaps most poetically, Voyager's crossing marked humanity's first direct contact with the galaxy's magnetic tapestry, a reminder that even as we orbit an ordinary star, we're forever intertwined with the Milky Way's invisible forces. This discovery fundamentally altered our understanding of the sun's domain. Rather than ending abruptly, the heliosphere's edge appears more like a porous shoreline, where solar and galactic magnetism mingle in an endless dance. As Voyager continues its lonely journey, now fully in interstellar space, each transmission carries new clues about how magnetic fields shape not just our cosmic neighborhood, but the very boundaries between stars. Among the thousands of exoplanets discovered beyond our solar system, one scorching world stands out as a potential cosmic battleground between atmosphere and stellar fury: HD 209458b. This gas giant orbits so close to its star that its atmosphere is literally boiling away, forming a comet-like tail of vaporized gas stretching over 200,000 kilometers. Yet something unexpected emerges from Hubble Space Telescope observations. Despite the brutal stellar onslaught, this planet seems to cling stubbornly to parts of its atmosphere, suggesting the presence of an invisible shield. Astronomers now suspect HD 209458b might harbor something no one expected to find on such a hellish world: a magnetic field powerful enough to deflect its star's deadly winds. The evidence comes from subtle distortions in the planet's evaporating atmosphere. As hydrogen gas gets torn away by stellar radiation, it doesn't escape evenly in all directions. Instead, Hubble detected clumps of gas trailing behind the planet in spiral patterns, as if caught in some unseen cosmic current. These structures align eerily with simulations of magnetized atmospheres, where charged particles get funneled along magnetic field lines rather than dispersing randomly. Even more telling, the planet's atmosphere appears to lose mass 10 times slower than similar worlds without magnetic protection. It's as if HD 209458b is wrapped in an invisible force field, fighting back against its star's attempts to strip it bare. How could a planet roasting at 2000 degrees Celsius maintain a magnetic field? The answer might lie in its interior dynamics. Unlike Jupiter, where metallic hydrogen generates magnetism through convection, this exoplanet's proximity to its star could create a different kind of dynamo. Tidal forces from the star's gravity might keep the planet's interior partially molten, with magma oceans circulating electrically conductive material. Alternatively, intense heat could ionize upper atmospheric layers, creating a secondary magnetic buffer through interactions with the stellar wind. Either scenario would produce a magnetic environment unlike anything in our solar system, a hybrid shield born from extreme stellar abuse rather than internal planetary processes. The implications ripple far beyond this single world. If magnetic fields can form on planets subjected to such brutal conditions, it dramatically expands the range of potentially habitable environments in the universe. A magnetic field could protect an Earth-sized exoplanet's atmosphere from erosion, even in close orbits around active stars, buying precious time for life to emerge. Future telescopes like the James Webb Space Telescope might soon detect the telltale radio emissions or atmospheric signatures confirming these exotic magnetic shields, opening a new chapter in our search for habitable worlds. HD 209458b stands as a cosmic rebel, defying expectations by clinging to its identity against all odds. A lesson that even in the universe's harshest neighborhoods, magnetism might write unexpected survival stories. The Moon today stands as a silent world without a global magnetic field, but its rocks whisper secrets of a far more dynamic past. Hidden in lunar samples brought back by Apollo astronauts, scientists discovered something astonishing: tiny mineral grains permanently magnetized billions of years ago, frozen in time like compass needles pointing to a long-lost north. These metallic fragments tell the story of an era when the Moon wasn't just Earth's companion. It was a magnetic powerhouse with its own churning core dynamo, generating a field possibly even stronger than Earth's is today. How could our airless, geologically quiet neighbor have ever sustained such a force? The answer lies in its fiery infancy. During the Moon's first billion years, its core likely remained molten from a combination of leftover formation heat and radioactive decay, with lighter elements like sulfur keeping the metallic soup stirring. As this liquid iron sloshed and swirled beneath the surface, it may have generated a self-sustaining dynamo similar to Earth's, just smaller in scale but proportionally more intense. Some models suggest tidal forces from a much closer Earth helped keep the lunar core active, stretching and kneading it like cosmic putty to maintain convection currents long after its size should have allowed it to cool. The most compelling evidence comes from Apollo-era basalt's lava flows that hardened between 3 and 4 billion years ago. When these rocks cooled, magnetic minerals within them aligned with the Moon's then active field, preserving its strength and direction like a cosmic snapshot. Modern measurements reveal these fields were surprisingly robust, up to 100 microteslas, roughly twice Earth's current surface field. Even more intriguing, different-aged rocks show the field persisted for over 1 billion years before gradually fading as the lunar core solidified. The timing correlates with the Moon's most volcanic period, suggesting its internal engine didn't just generate magnetism, it powered widespread geological activity we now see frozen in the Maria's dark plains. Yet the Moon's magnetic history holds puzzles. Some regions, like the Rhein Gamma swirl, those bizarre bright patches visible through backyard telescopes, display localized magnetic anomalies strong enough to deflect solar wind particles, creating miniature protective bubbles. These could be remnants of the ancient global field, preserved in crustal rocks rich in iron-bearing minerals. Alternatively, they might stem from later impacts that vaporized iron-rich meteorites, temporarily magnetizing surrounding material. Either way, they hint at complex magnetism persisting even after the core dynamo shut down, a ghostly echo of the Moon's more active youth. What caused the dynamo's eventual death? The likely culprit is simple cooling. Unlike Earth, with its massive core sustained by ongoing radioactive heating and compositional convection, the Moon's smaller size doomed its internal engine. As iron crystals began forming at the core mantle boundary, they disrupted the convective patterns needed to sustain the magnetic field. Within a few 100 million years, the once mighty lunar field dwindled to nothing, leaving the surface exposed to the full brunt of solar and cosmic radiation. A key reason why the Moon's regolith became so heavily charged and chemically altered over time. This discovery rewrites our understanding of lunar evolution. No longer just a static relic, the Moon emerges as a world that underwent dramatic internal changes. A place where rivers of lava once flowed under the protection of a now vanished magnetic shield. Its story mirrors what might await Mars and other rocky worlds as their cores slowly freeze. A transition from geologic vibrancy to quietude, with only magnetized rocks left to testify to their vanished dynamos. For planetary scientists, these lunar magnetic fossils offer more than just history. They provide clues about how small bodies generate and lose global fields, helping us predict which distant exoplanets might still shelter protective magnetospheres around dim, cooling stars. The next time you gaze at the Moon's tranquil face, remember, those gray plains hold evidence of an ancient cosmic storm, a time when Earth's companion wasn't just reflecting sunlight, but generating invisible forces of its own, shaping the environment of early worlds in ways we're only beginning to understand. Deep in Earth's ancient past, long before continents took shape or oxygen filled the skies, our planet's magnetic field may have played a hidden starring role in the drama of life's origins. 4 billion years ago, the Sun wasn't the relatively stable star we know today. It was a tempestuous newborn, unleashing solar storms 100 times more powerful than anything modern instruments record. Without protection, these blistering particle winds would have scoured Earth's surface, stripping away volatile molecules essential for life's delicate chemical experiments. Yet somehow, amid this cosmic bombardment, the first self-replicating molecules emerged. The question dividing scientists is whether Earth's early magnetic field acted as an invisible guardian, creating safe zones where life's fragile building blocks could accumulate without being torn apart by radiation. Some researchers point to banded iron formations, rust-colored mineral deposits dating back 3.8 billion years as potential smoking guns. These swirling layers of iron oxide suggest Earth already had a functioning dynamo core, generating a global magnetic field strong enough to deflect charged particles and prevent atmospheric erosion. Laboratory experiments back this up, showing that amino acids, the precursors to proteins, form more efficiently when shielded from ultraviolet radiation and cosmic rays. In magnetic field simulations mimicking early Earth conditions, organic molecules like ribonucleic acid strands survive 10 times longer than in exposed environments. The field wouldn't have needed to be as strong as today's. Even a partial shield could have created localized nurseries around hydrothermal vents or tidal pools where chemistry could progress uninterrupted. But not all evidence aligns neatly. Some astrobiologists argue that magnetic fields might have been a double-edged sword. While protecting the atmosphere, they also deflect cosmic rays, particles that could have provided energy to drive prebiotic reactions. Certain meteorite studies reveal complex organic molecules formed in deep space without any magnetic shielding, suggesting life's ingredients might be hardier than we assume. There's even a controversial theory that transient field collapses allowed periodic bursts of radiation to reach the surface, acting as a cosmic stir stick that accelerated mutation rates in early replicators. The debate extends beyond Earth. Mars' lack of both a strong magnetic field and persistent life offers a cautionary comparison, yet Venus, despite its present magnetic weakness, shows evidence of having lost its water through other mechanisms. Meanwhile, Jupiter's moon Europa, shielded by its host planet's enormous magnetosphere, demonstrates how magnetic protection can maintain liquid oceans under an ice shell despite minimal sunlight. These cosmic examples suggest magnetism's role in life's origins may not be absolute but situational, a facilitator rather than a strict requirement. What tilts the scales toward Earth's field being pivotal? The timing. The oldest known fossils coincide with periods when geomagnetic studies suggest the dynamo was stabilizing after early turbulence. During the late heavy bombardment 4 billion years ago, when asteroids rained down relentlessly, a magnetic field could have prevented Earth from becoming as desiccated as Mars by retaining atmospheric water vapor. And crucially, magnetism may have enabled Earth to keep its hydrogen, a key ingredient for early metabolic processes, from being stripped away by solar winds, something we observe happening to unprotected planets today. The answer likely lies somewhere in between. Earth's magnetic field probably didn't single-handedly allow life to emerge, but by creating stable environments where organic chemistry could persist across millennia, it may have tipped the odds in life's favor. In the grand casino of cosmic probabilities, magnetism gave Earth's primordial soup something invaluable: time. Time for random interactions to become patterns, for simple compounds to complexify, and for chemistry to cross the mysterious threshold into biology. Whether this makes magnetic fields a universal prerequisite for life or just one piece of Earth's unique puzzle remains one of astrobiology's great open questions, one that future missions to icy moons and exoplanets may help unravel. When black holes devour matter, conventional wisdom suggests they destroy information entirely, swallowing stars, planets, and light without leaving a trace beyond mass, spin, and charge. But Einstein's equations hint at a far stranger possibility. Black holes might grow magnetic hair, delicate filaments of force that could preserve echoes of everything they've consumed. Picture the event horizon not as a smooth, featureless boundary, but as a surface etched with invisible grooves and ridges, subtle distortions in spacetime where magnetic fields anchor themselves like cosmic roots. These hypothetical structures could encode details about a black hole's history, defying the long-held assumption that these gravitational monsters are the universe's ultimate shredders. The theory hinges on an obscure prediction from general relativity called no-hair theorem, which ironically suggests black holes should be bald, characterized only by 3 simple traits. Yet recent simulations reveal that when magnetic fields thread through collapsing matter, they don't just vanish behind the event horizon. Instead, they freeze into place, imprinting the black hole's surface with intricate patterns resembling the magnetic fields of the swallowed material. Imagine dunking a magnet into liquid nitrogen. The field lines don't disappear, they become locked in place. Similarly, a star's magnetic fingerprint might persist on a black hole's horizon long after the star itself is crushed into oblivion. This hair isn't made of matter but of twisted spacetime itself. As charged particles spiral into a black hole, their magnetic fields stretch and twist like taffy, creating permanent kinks in the fabric of reality. Advanced models show these disturbances could survive for eons, subtly altering how the black hole interacts with surrounding plasma. In 2016, physicists even calculated that such magnetic hair might generate measurable gravitational waves, ripples that future observatories could detect as faint whispers in the cosmic background. The implications rewrite black hole thermodynamics. If magnetic hair preserves information, it could resolve Stephen Hawking's famous paradox about whether data is truly lost in these voids. A black hole might not erase the origin of its dinner after all. It could simply encode it in a language of space-time warps and magnetic braids we're only beginning to decipher. Yet the theory remains controversial. Some argue these magnetic imprints would be too faint to matter, or that quantum effects at the horizon would scramble any meaningful data. Others counter that even subtle fields could accumulate over time, like grooves on a vinyl record, creating a celestial archive of everything the black hole consumed. The search for evidence is already underway. Telescopes study how plasma behaves near supermassive black holes, looking for asymmetries that might betray hidden magnetic structures. Meanwhile, theorists explore whether this hair could explain mysteries like fast radio bursts or unexpected X-ray flares. One thing is certain: if magnetic hair exists, it reveals black holes as cosmic librarians rather than anarchists, not just crushing information but curating it in spacetime's most alien language. Mercury shouldn't have a magnetic field. At least that's what scientists thought before NASA, a messenger probe, began orbiting the tiny planet in 2011. Smaller than Jupiter's moon Ganymede and only slightly larger than Earth's moon, Mercury's modest size suggested its core should have cooled and solidified billions of years ago, shutting down any planetary dynamo capable of generating a global magnetic shield. Yet as Messenger skimmed just 200 kilometers above Mercury's scorched surface, its magnetometer detected something astonishing: an active magnetic field, weak but unmistakable, stretching hundreds of kilometers into space like a tattered cloak barely clinging to the planet's shoulders. This discovery upended decades of planetary science. Earth's robust magnetic field arises from its churning molten iron core, but Mercury's interior was presumed too small to retain enough heat for such activity. The key to the mystery lies in an unexpected layer deep within the planet, a partially molten outer core that somehow avoided freezing solid despite Mercury's proximity to the Sun's relentless heat. Messenger precise gravity measurements revealed the planet's core makes up a staggering 85% of its radius, with the outer 1,500 kilometers remaining liquid. This bizarre composition suggests Mercury's core contains lighter elements like sulfur mixed with iron, acting like antifreeze to maintain convection currents even in extreme conditions. But the surprises didn't stop there. Mercury's magnetic field isn't just weak, it's lopsided. Unlike Earth's relatively symmetrical dipole field, Mercury's magnetic axis is offset northward by nearly 20% of the planet's radius. This creates an asymmetry where the magnetic field over the southern hemisphere is 3 times stronger than in the north. Messenger observations showed solar wind particles can actually penetrate close to the surface near the equator, where the field is weakest, bombarding the terrain with charged particles that may contribute to Mercury's mysterious, hollow, bright, irregular depressions where volatile materials appear to have sublimated into space. How does such a small world maintain this magnetic oddity? One compelling theory involves the core's unique crystallization process. As Mercury's inner core slowly solidifies, lighter elements like sulfur get excluded from the growing metallic lattice, creating buoyant plumes that rise through the outer core. This compositional convection, combined with the planet's surprisingly rapid rotation, one spin every 59 Earth days, might generate just enough organized motion to sustain a dynamo. Computer simulations show these conditions could produce a weak, asymmetric field matching messenger observations, though some researchers argue tidal forces from the Sun's gravity might also stir the core like a cosmic spoon. The implications stretch far beyond our solar system. If tiny Mercury can defy expectations and maintain an active magnetic field billions of years after formation, countless exoplanets orbiting close to their stars might do the same, potentially preserving atmospheres against stellar winds despite their small size. ESA's BP Colombo mission, currently orbiting Mercury with even more sensitive instruments, is now hunting for clues about how long this magnetic shield can last. Its measurements could reveal whether Mercury's dynamo is stable or flickering toward eventual collapse, providing a glimpse into the future of other magnetized worlds both in our cosmic backyard and among the stars. Mercury's stubborn magnetism serves as a humbling reminder that even the smallest planets can harbor grand surprises. What other secrets might this scorched world reveal about the delicate balance of heat, motion, and chemistry that transforms a cooling rock into a dynamic magnetic entity? As we continue to study this enigmatic planet, one thing becomes clear. In the cosmic dance of magnetic fields, size matters far less than we ever imagined. Before stars or galaxies even existed, in the universe's first turbulent moments, the seeds of cosmic magnetism may have already been sown. Scientists now trace these primordial magnetic fields through an unexpected messenger: the faint polarization of light from quasars billions of light years away. These brilliant beacons, powered by supermassive black holes, act as cosmic backlights, illuminating magnetic fingerprints imprinted on the fabric of space itself during the universe's infancy. The story begins just microseconds after the Big Bang, when the universe was a seething plasma of charged particles too hot for atoms to form. In this primordial soup, slight density variations created ripple sound waves traveling at half the speed of light. Theorists suggest these waves could have generated weak magnetic fields through a process called the Biermann battery effect, where turbulent plasma motions twist free electrons into microscopic currents. The resulting fields would have been vanishingly faint, billions of times weaker than Earth's, but stretched across the entire observable universe as space expanded. For decades, these primordial fields remained purely hypothetical. Then came breakthrough observations of distant quasars like 3C286. As their light traverses the cosmic web, it interacts with ancient gas clouds magnetized during the universe's first billion years. This subtly rotates the light's polarization, an effect called Faraday rotation, revealing both the strength and geometry of intervening magnetic fields. Astonishingly, even regions far from any galaxy show coherent magnetic structures, suggesting these fields predate star formation itself. Some of the most compelling evidence comes from the illustrious Tingy supercomputer simulations, which model how tiny seed fields could have amplified over cosmic time. The simulations show these weak initial fields getting stretched and twisted by collapsing galaxies and supernova shocks, eventually growing into the microgauss strength fields we observe today. Remarkably, they predict the same large-scale magnetic patterns now being detected in intergalactic voids, like finding the same signature on a fingerprint across 13 billion years of cosmic evolution. Yet mysteries persist. Some quasars exhibit polarization patterns suggesting magnetic fields were already surprisingly organized when the universe was less than 2 billion years old, too soon for galaxy formation alone to explain their structure. This has led to alternative theories, including phase transitions in the early universe's fundamental forces that might have generated magnetic defects in spacetime itself. Others speculate that primordial black holes or cosmic strings could have jump-started magnetism on cosmic scales. The implications rewrite our understanding of cosmic evolution. These ancient magnetic fields may have guided the collapse of the first gas clouds, determining where stars and galaxies could form. They could also explain how cosmic rays accelerate to such extreme energies, riding magnetic shockwaves that have been propagating since the dawn of time. Most remarkably, they hint that magnetism isn't just a local phenomenon. It's woven into the universe's very architecture, a relic from an era when reality itself was being forged. As next-generation telescopes like the Square Kilometre Array come online, they'll map these primordial fields in unprecedented detail, potentially uncovering their true origins. What they reveal could answer one of cosmology's greatest remaining questions: whether magnetism emerged from chaos in the universe's first moments, or if it was written into the laws of nature from the very beginning. What if magnetism isn't just a byproduct of stars and planets, but a fundamental feature of the cosmos woven into the universe's blueprint from the very first moments of existence? This radical idea, known as the magnetic universe theory, suggests that magnetic fields didn't emerge later from churning metals or stellar dynamos. They were there at creation, imprinted on spacetime like invisible cosmic graffiti. Proponents point to distant quasars whose light carries traces of magnetism in regions so ancient, no stars or galaxies had yet formed to generate fields the conventional way. These primordial whispers, faint but detectable, hint that magnetism might be as intrinsic to the universe as gravity or light. Consider the implications. If true, magnetism wouldn't just shape galaxies, it could have guided their very formation. In the early universe's primordial plasma, even weak magnetic fields would have acted like cosmic scaffolding, nudging gas clouds into the filaments and voids we now see in the large-scale structure of the cosmos. Simulations show how these seed fields, amplified by collapsing matter and turbulent plasma, could evolve into the intricate magnetic webs observed in galaxy clusters today. It's as if the universe's invisible skeleton has been magnetic all along, quietly directing the growth of cosmic architecture while remaining hidden in plain sight. The boldest versions of this theory go even further. Some physicists speculate that these primordial fields might stem from exotic phase transitions in the universe's first trillionth of a second, when fundamental forces like electromagnetism and the weak nuclear force split apart. Just as water freezing into ice creates cracks, this cosmic symmetry breaking could have spawned defects in spacetime itself, generating magnetic monopoles or eternal cosmic strings that stretched into vast magnetic domains. Others propose that quantum fluctuations during inflation, the universe's exponential expansion, stretched subatomic magnetic wrinkles to intergalactic scales, like pulling taffy, until microscopic imperfections become continent-sized grooves. Yet skepticism remains. Critics argue that observed intergalactic fields could still originate from later astrophysical processes leaking from early galaxies or ejected by quasars. The challenge lies in distinguishing truly primordial magnetism from contamination by later cosmic events. Future telescopes like the Square Kilometre Array aim to settle the debate by mapping the universe's magnetic fossil record in unprecedented detail, searching for patterns that betray a primordial origin. If they find coherent magnetic structures in the cosmic voids, regions untouched by galaxies or supernovae, it would be smoking gun evidence for the magnetic universe. What's at stake isn't just academic. Primordial magnetism could rewrite our understanding of cosmic evolution, revealing how the universe transitioned from smooth plasma to structured complexity. It might even explain anomalies like the mysterious axis of evil, an unexpected alignment in the cosmic microwave background that some theorists link to large-scale magnetic influences. Whether the theory holds or falls, it forces us to confront a profound question. Is magnetism merely a local phenomenon, or is it threaded through the cosmos itself, as fundamental as space and time? The answer could redefine our place in a universe where invisible forces shaped everything from the first stars to the spiral arms of our own Milky Way. Dark matter remains the universe's most elusive ghost, an invisible substance outweighing ordinary matter 5 to 1, yet refusing to interact with light or magnetic fields as far as we can detect. But what if this cosmic phantom isn't entirely magnetically silent? Emerging theories suggest the vast halos of dark matter enveloping galaxies might harbor faint magnetic fields of their own, woven into their mysterious fabric in ways we're only beginning to imagine. These wouldn't be the intense fields of neutron stars or the orderly spirals of galactic disks, but something far subtler: cosmic whispers threading through the darkness, gently nudging the universe's largest structures into shape. The idea stems from dark matter's gravitational influence on ordinary matter. As galaxies form, their visible gas and stars sink into the gravitational wells of dark matter halos, dragging ionized plasma along for the ride. This plasma carries magnetic fields, weak ones but persistent, that could theoretically imprint onto the surrounding dark matter environment through gravitational interactions alone. Simulations show that even if dark matter particles don't directly respond to magnetism, their movements might align with these background fields over billions of years, creating large-scale patterns akin to ion filings scattered near a magnet. The resulting dark magnetism wouldn't behave like conventional fields. It might lack polarity or the ability to accelerate particles, but it could still subtly guide the collapse of gas clouds during galaxy formation. Consider the bullet cluster, where collisions between galaxy clusters have visibly separated dark matter from luminous matter. X-ray observations reveal turbulent magnetic fields in the displaced gas, while gravitational lensing maps the dark matter's distribution. Intriguingly, the dark matter's geometry shows faint filamentary structures that mirror magnetic field lines in ordinary matter, an echo that some theorists interpret as evidence of indirect magnetic influence. If verified, this would mean dark matter halos don't just provide gravitational scaffolding for galaxies, they might also preserve a fossil record of primordial magnetic turbulence from the universe's youth. The mechanisms behind such fields could be stranger than anything in textbook physics. Some models propose that dark matter particles, if they possess even a tiny electromagnetic charge, 1/1000th of an electron or less, might generate weak magnetic dipoles through quantum effects. Others suggest action-like particles. Hypothetical dark matter candidates could interact with ordinary magnetism to create hybrid action photon fields permeating halos. These wouldn't be detectable with current instruments, but might leave imprints on cosmic microwave background polarization or subtly alter the trajectories of high-energy particles passing through galaxy clusters. The implications ripple across cosmology. If dark matter halos have magnetic personalities, it could explain why galaxies in certain environments develop unexpectedly strong magnetic fields early in their histories. These hidden influences might also resolve anomalies in cosmic ray propagation. Some ultra-high-energy particles arrive from directions that seem to align with dark matter filaments, as if their paths were gently steered by invisible magnetic guides. Even more tantalizing is the possibility that primordial dark magnetism played a role in the universe's first moments, seeding the large-scale structure we see today. Yet skepticism persists. Detecting magnetic fields without charged particle interactions seems to defy electromagnetic theory, and alternative explanations, like unseen baryonic matter or systematic errors in galactic rotation curves, could account for the anomalies. Future experiments like CMB-S4 or the Square Kilometre Array aim to test these ideas by searching for unique polarization signatures in light-traversing dark matter-dominated regions. A confirmed detection would revolutionize our understanding of both dark matter and cosmic magnetism, revealing them not as separate phenomena but as intertwined forces shaping the cosmos from the shadows. Until then, the notion of magnetic dark matter halos remains a captivating frontier, a reminder that the universe's greatest mysteries often lurk not in the light, but in the delicate interplay of forces we've yet to fully comprehend. Whether these hidden fields exist or not, their theoretical exploration stretches our imagination, challenging us to envision a cosmos where even the most elusive substance might dance to magnetism's silent tune. The sun doesn't just shine, it twists itself into magnetic knots so complex they'd make a sailor's rope look like a child's shoelace. These colossal structures, called solar prominences, arc hundreds of thousands of kilometers above the sun's surface, held aloft by coiled magnetic fields carrying enough energy to power human civilization for millennia. Picture a colossal bridge made of pure magnetism, its strands braided tighter than steel cables under unimaginable tension until suddenly, catastrophically, they snap. What makes these magnetic ropes so extraordinary is their duality. They can cradle plasma hundreds of times denser than the surrounding corona for weeks or months, suspended in graceful loops that would dwarf entire solar systems. Yet the same structures become cosmic tripwires, storing energy until critical thresholds are crossed. When the sun's turbulent surface motions overwind these magnetic coils beyond their breaking point, the result is one of the most violent releases of energy in the solar system, a coronal mass ejection. The unraveling happens in stages. First, individual strands break, releasing torrents of superheated plasma. Then the entire rope structure recoils like a severed elastic band, catapulting billions of tons of magnetized gas into space at millions of kilometers per hour. NASA's Solar Dynamics Observatory has captured this drama in astonishing detail. Time-lapse sequences show dark plasma filaments writhing along these magnetic channels like snakes trapped in an invisible cage before the inevitable eruption. The most powerful events, like the Bastille Day flare of 2000, send shockwaves through the entire heliosphere, their impact measurable on Earth through radio blackouts, satellite disruptions, and intensified auroras reaching unusually low latitudes. What looks like chaotic destruction actually follows precise magnetic principles. The breaking ropes realign into simpler configurations, releasing energy through processes identical to those powering experimental fusion reactors, just on scales 1 trillion times larger. These eruptions don't just demonstrate raw power, they reveal fundamental cosmic physics. The twisting motions preceding eruptions match laboratory plasma experiments, confirming that the same magnetodynamic laws govern both kitchen-sized fusion devices and star-spanning explosions. Solar physicists have even identified telltale signatures in the rope's spiral patterns that predict eruption likelihood, much like counting twists in a rubber band before it snaps. Some prominences develop double-decker structures with multiple twisted layers, a configuration that stores extra energy and often leads to the most geo-effective CMEs when it finally detonates. Yet mysteries remain. Why do some twisted ropes stabilize for months while others explode within hours? How do the thinnest strands, some barely wider than Earth, survive temperatures exceeding 1 million degrees? The answers may lie in the sun's mysterious lower atmosphere, where new telescopes like the Daniel K. Inau Solar Telescope are revealing previously invisible magnetic braids constantly feeding energy into the corona. Each observation peels back another layer of complexity, showing our star not as a smooth ball of gas, but as a seething fractal of magnetic threads where every loop, kink, and snap reshapes the space around us. One thing is certain: when these cosmic ropes finally break, they don't just vanish. Their debris becomes part of the solar wind, carrying imprints of the sun's magnetic fingerprint across the solar system, and occasionally right to our doorstep. The next time you see auroras dancing overhead, remember, You're witnessing the afterlife of a magnetic structure so vast it once bridged the sun's churning surface and its scorching outer atmosphere, now painting Earth's skies with its final, brilliant unraveling. The frontier of cosmic magnetism is about to be revolutionized by a new generation of space missions, equipment so sensitive they could detect the magnetic heartbeat of a neutron star from across the galaxy. Leading this charge is the European Space Agency's LISA mission, set to launch in the mid-2030s. Unlike traditional telescopes, LISA won't rely on light. It'll sense gravitational ripples from collisions between magnetars, those ultra-magnetic stellar corpses capable of warping space-time itself with their explosive starquakes. Picture this: when two magnetars spiral into each other, their entangled magnetic fields don't just vanish, they convert into gravitational waves with a unique signature, a cosmic fingerprint LISA triangular array of spacecraft can decode from billions of light-years away. These events could reveal how magnetic fields behave under conditions so extreme they momentarily rival the Big Bang's energy density, offering clues about quantum gravity and the fundamental nature of spacetime. Meanwhile, NASA's Interstellar Mapping and Acceleration Probe (MAP) aims to chart the solar system's magnetic highways with unprecedented precision. Slated for a 2025 launch, this spacecraft will orbit at Lagrange Point 1, a gravitational sweet spot between Earth and the Sun, where it'll analyze how charged particles surf on interplanetary magnetic fields. But a MAP real prize is mapping the heliospheric current sheet, that vast, wavy boundary where the Sun's magnetic field flips polarity, creating a ripple effect stretching beyond Pluto. These observations could solve long-standing mysteries, like why some cosmic rays get funneled toward Earth along magnetic channels while others mysteriously vanish. Equipped with 10 cutting-edge instruments, a map will essentially create three-dimensional magnetic weather maps of our solar neighborhood, predicting how geomagnetic storms propagate and how the solar wind's magnetism shapes planetary atmospheres over millennia. Not to be outdone, Japan's upcoming Space Infrared Telescope for Cosmology and Astrophysics (SPICA) plans to peer through cosmic dust clouds using far-infrared spectroscopy, tracing magnetic fields in stellar nurseries where telescopes like Hubble see only darkness. By measuring how dust grains align with magnetic fields, SPICA could uncover how these invisible forces guide the birth of stars and planets. Early tests suggest it might even detect the weak magnetic imprint left over from the universe's first galaxies, fossilized magnetism from an era when the cosmos was just learning to glow. The most daring experiment of all might be the proposed Plasma Observatory, a fleet of satellites designed to study magnetic reconnection, the explosive snapping and reconnecting of field lines in Earth's own magnetosphere. By capturing this process at electron-scale resolution, scientists hope to crack the code of how magnetic energy transforms into particle acceleration, a universal mechanism powering everything from solar flares to distant quasars. Success could lead to breakthroughs in fusion energy, as tokamak reactors on Earth struggle with the same unstable magnetic phenomena that the cosmos mastered billions of years ago. Together, these missions form a coordinated assault on magnetism's greatest mysteries. From the quantum knots inside neutron stars to the magnetic webs connecting galaxies, we're finally building tools to see the universe not just as a collection of objects, but as a dynamic tapestry of invisible forces. Each dataset will be like adding a new color to our cosmic palette, revealing patterns and connections no single instrument could uncover alone. The golden age of magnetic exploration isn't coming, it's already here, and its discoveries promise to rewrite textbooks from astrophysics to quantum mechanics. What we learn may not just illuminate the cosmos, but redefine our place within it. From the crushing magnetic prisons of neutron stars to the delicate cosmic webs guiding galaxy formation, we've journeyed through 30 astonishing truths about the universe's most extreme magnetic fields. These invisible forces don't just shape matter, they rewrite the rules of physics, turning the vacuum of space into a canvas where particles dance to magnetism's tune. Imagine stellar corpses so magnetized they warp atoms with a glance, or sunspots with fields strong enough to halt a speeding bullet mid-flight. Picture black holes growing magnetic hair that preserves their violent histories, or protostars weaving planets from magnetized dust. Every corner of the cosmos whispers magnetic secrets, whether it's Mercury's improbable dynamo, Venus's atmospheric hemorrhage, or the Milky Way's sprawling magnetic skeleton holding our galaxy together. Magnetism is more than cosmic decoration, it's the universe's silent architect. Without it, stars might never ignite, planets could lose their atmospheres, and life itself might never find shelter from lethal radiation. The same force that guides a compass needle on Earth also sculpts relativistic jets screaming from supermassive black holes, fuels solar storms that knock out power grids, and may even have cradled the molecules that sparked life. From the quantum vortices inside neutron stars to the intergalactic highways carved by magnetic reconnection, we've seen how fields of force dictate the fate of everything, turning chaos into structure, destruction into creation. Now, we'd love to hear which of these magnetic marvels shocked you most. Was it the magnetar flare that outshone the Milky Way, or the diamond planet forged by pulsar winds? Maybe you're still reeling from the thought of Jupiter's magnetic tail brushing Saturn, or the eerie possibility that dark matter halos harbor ghostly magnetic imprints. Drop your favorites in the comments and tell us what cosmic mystery we should explore next. Should we dive deeper into black hole magnetism, or unravel the enigma of primordial magnetic fields from the Big Bang? Before you go, hit that like button if you enjoyed this magnetic odyssey. It helps us bring you more mind-bending space content. And don't forget to subscribe so you never miss a journey into the universe's greatest wonders. Until next time, keep looking up, because out there, beyond our sight, invisible forces are still bending reality to their will. Who knows what we'll discover when we finally learn to see the cosmos through magnetism's eyes?